Testing with a lab scope. Now there's many systems and components that can be tested with the lab scope. Using the DSO correctly is the key to diagnosing with it. Make sure you have studied and you understand how to set the DSO up so the waveforms can be viewed correctly. Use a vehicle-specific wiring diagram to determine the test points. It's very important because when you're testing things like a injector and you want to get a voltage waveform and you're supposed to go on the ground side with a voltage probe, well, what color is that wire? Which cavity is it you're going to probe into? So a vehicle-specific wiring schematic is a must. With injector testing, you can view the voltage waveform, or you can view the current waveform, which is a low current probe around the power or the ground side of the injector. Now here's a voltage waveform for an injector. And when you look at it, you can see that part of the waveform that represents the charging system. You can see the on time, how long the injector is on by using your cursors. And of course, you can measure the inductive kick to determine are the windings in the injector normal. Here is an injector current waveform. You can measure with your cursors the current being drawn by the injector. And don't forget, you should see some type of pindle hump. Now this is an excellent pindle hump on this waveform. All injectors don't have a pindle hump that is that obvious. Sometimes it's very difficult to see, but just make sure it's there. And here we're just comparing the voltage injector waveform to the current injector waveform. And you can see that as the current starts to flow there in the blue, that's when the injector goes on. And when the current gets turned off, that's when the injector has its inductive kick. Oxygen sensor waveform has a lot of information that can be used for diagnostics. Now connect the oxygen sensor's signal circuit to your voltage probe on your DSO. Now this is two oxygen sensor signals. We'll talk about this in a minute. The red one is the oxygen sensor that is behind the catalytic converter. The blue one is the fuel control sensor, or the one in front of it, and that's the one we're going to talk about now. Most oxygen sensors work between minus 75 millivolts and 1.2 volts. The oxygen sensors are tested for things like voltage, amplitude, and switching. Switching, or the speed of the oxygen sensor, is really the most overlooked part of oxygen sensor diagnostics. In the waveform on the green trace, you can see that we've snapped the throttle 3 times in a row. Then we've drawn a red line, indicated by the red arrow pointing to it, right next to where the oxygen sensor voltage started to rise. Now the first snap we did a really good job, and you can see that the oxygen sensor responded quickly. In the second one we did a half good job, it didn't respond so fast. And in the third one we did a poor job. We're trying to depict to you very, very fast on the left and then slow on the right. Now the oxygen sensor reaction speed can't be measured or seen in scan data. And we're going to show you here that the fast sensors on the left and the slow sensors on the right, a slow sensor should be changed. If you snap the throttle, it doesn't go up instantaneously, then it's a slow sensor and it needs to be replaced. This is a perfect oxygen sensor waveform. And I say that, but it's probably almost perfect. Nothing's perfect, right? But this particular oxygen sensor waveform has been used by us at the Research Center for years to show you what perfect should look like. Now, when you look at the tops, or the rich side of the oxygen sensor, it can help determine things like basic engine condition, leaking EGR, too rich conditions. And that's important because just looking at the oxygen sensor can tell you, hey, I got to go do an EGR test. I have to go do a compression test. Now, when you see spikes like these, that's an indication that a cylinder is having a misfire. In this case, it's not telling you which cylinder, but it knows you have to go check and with an ignition scope and find out which cylinder is misfiring. Now, oxygen sensors have heater circuits, and they can be tested with the lab scope. Connect to the oxygen sensors B+ for that heater circuit. Now, we've chosen a complicated, if you will, heater circuit. This is a Chrysler heater circuit, and we're using 3 channels there. And at the top, that's actually the control circuit. That is the computer circuit to the oxygen sensor heater, where it's pulsing it on and off to heat the oxygen sensor up. And then, of course, there's B+. And down here is the current flowing. We've done that with a low current probe. And you can see every time the green trace goes on and off, we get a pulse of current to the oxygen sensor heater. So we can use this as an example of, hey, you can get a lot of stuff out of an oxygen sensor heater circuit. Now, GM and Ford, they don't have the control type that you see here, and basically you would use a low current probe and then, of course, test battery power to it. Catalytic converter testing, the front and rear oxygen sensors can be viewed on 2 different channels to show catalytic converter efficiency. You're going to connect one channel to the front oxygen sensor signal circuit and the second channel to the rear oxygen sensor signal circuit. And we're going to see that same waveform we saw earlier. And what you're looking at now is what the computer looks at for the catalytic converter monitor. The fuel control sensors in the blue, the rear oxygen sensors in the red, and you can see that they tell you that the rear oxygen sensor should basically be flat. It doesn't say it should be high rich or low lean or somewhere in the middle. It's just saying it should be flat. And what they say is when the rear oxygen sensor begins to take on the appearance of the front oxygen sensor, the catalytic converter is not being efficient. Sensor testing, sensors like MAFs can be tested with the lab scope. And you're going to connect to the sensor signal circuit. In this case, we're going to show you a MAF, so we're going to connect to the MAF's signal circuit. And this is a Ford MAF, mass airflow, and you see it's going along there, and we snap the throttle, and it should go through to a certain voltage level. And if you have a digital mass airflow, like on a GM, you should see the digital signal. Ignition testing, well, lab scopes are just made for ignition testing. You can do so much with them. You can look at primary voltage, and that's a voltage probe to the control side of the coil. You can look at primary current, and that's a low current probe to the control side of the coil. And of course, you can look at secondary, which is an inductive probe to the secondary wire, or in some cases, we can use an adapter. Now, this is a primary voltage signal, and you can see that it has a lot of information in it. It starts off on the left, and then we have coil turn on, then we have our inductive kick, and then we have our firing line, then we get our oscillations. Well, you see the same thing in secondary voltage. They don't look that different, do they? In fact, if we lay one over the other, you can see they both look very similar. If you do not have secondary adapters for your DSO, then you can look at primary voltage and see the same thing. Now, you can look at primary current with a low current probe. In that case, you would adjust the sweep rate so you can see all the coils' activity. In this case, it's a 6-cylinder. There's 3 coils. We see 3 coils. They're all even. They look the same. So that looks good to us. Then we'll adjust the sweep rate so we can just view one coil. And you can see our cursor is going to measure current. And then we're going to change our cursors to measure rise time. And that is going to help us determine the condition of that coil. And once again, we have both. We have the current waveform in the blue and the voltage primary in the red. And you can see that when the coil gets turned on, that's when current, or the blue, starts to rise. And then when the current gets turned off, that's when we get our inductive kick. Some cars like Ford's have a multi-strike. So if you're using a low current probe and you're looking at primary current, you'll see all 3 strikes. Wheel speed sensors. You can connect the DSO positively to one side of the sensor and a negatively to the other side, and then you can operate the vehicle. And in this case, we have two channels, a blue channel and a red channel, channel 1, channel 2, or in some cases, channel A, channel B. And we can see that the wheel speed sensors, the faster the wheel turns, the more events you can see. But you can see they're all even. That's the main part. And then the faster the wheel goes, the more events you can see without any dropping out. GM's coil near plug is kind of a unique ignition system, so you can connect a voltage lead to the coil's control circuit. You can connect a low current probe around the coil's B+, and you can also use a third channel if you have it for an inductive probe around the secondary wire, and you're going to get this waveform. The blue is the computer's control of that coil, turning it on, commanding it on and off. The red is the primary current going through that coil. You can see when the command tells it to turn on, current starts to rise. When it tells it to turn off, when the blue goes back down on that falling edge underneath the red there, you can see that's when the current gets turned off. And if you have more than two channels, you can of course have that secondary ignition signal on the screen with you, and you can see it's doing the same thing as the others. Transducers. Now these can be placed in tailpipes, spark plug holes, intake manifold, fuel rail. You're going to want to follow the manufacturer's instruction for use of those transducers. But in the case like this, we have a cranking 4-cylinder engine. The red probe is a secondary sync probe connected to the number 1 cylinder, and the blue is the signal coming off the transducer. And you can see that it's representing 4 different cylinders, and in this example they all look alike, so that means they're all even compression cylinders. And you can put these pressure transducers anywhere you want. Here's one on the intake manifold, and once again we have a secondary ignition signal in the red on cylinder number 1, and we see the same 4 cylinders, and we can see our intake pulses are the same, telling us we have a pretty good basic engine. Now PM or permanent magnet crankshaft position sensors like that on a Ford, you're going to connect the DSOs positively to one side of the sensor and the negatively to the other side of the sensor, and you can run the engine, or well, I guess you can run the engine, and then you're going to see this signal in the red, and that's the permanent magnet crankshaft position sensor for Ford. We also, in the blue, put a secondary ignition signal in there, and that's showing us, and we all know that the ignition fires a few degrees before top dead center, and we can see that we have a secondary ignition firing a few degrees before that one event that looks different, and that's the signature pulse. So we can see that our ignition is firing correctly. Solenoids, all you got to do is connect a voltage probe to the ground side of the solenoid. Here's a solenoid like a Ford's IAC solenoid, and you can see the pulses there. You can see where it makes a few changes, and here it's in the holding position. IAC motors, like IAC on most vehicles, it's a stepper motor. You're going to connect the voltage probe to the control side of the motor, and here's the waveform for that. You can see it's charging system voltage, and it's a pulse. It's not a steady state. It's holding that motor in a certain position. NOx sensors, connect the voltage probe to the NOx sensor signal circuit, and then of course you're going to have to tap on the block near the NOx sensor to get a signal like this. If you get a signal like this and you're not tapping, then you have engine knock. Duty cycled solenoids, you go ahead and connect the voltage probe to the control side of the solenoid just like you do normally, and here we can see that the computer is turning this solenoid on a very small amount of the time. Down there at the bottom, it's mostly off up there on the top. Hall effect sensors, connect the voltage probe to the sensor signal circuit, and here we have a GM's Hall effect. You can see its charging system voltage, or B+, and here we can see it's evenly paced, and you can learn to use your DSO and put a signal up here like a cylinder number 1 sync probe, and then you can count the pulses in between every time number 1 fires and ensure that all the pulses are present and even. Fuel pumps, use a low current probe around the B plus or the ground side of the pump. It's a simple circuit. Whatever amps are going to go in the pump is going to come out of it. And you get a signal like this. There's a lot of testing you can do with a fuel pump and a low current probe. EGR Control Solenoid, as with any solenoid, connect the voltage probe to the ground side and you get an image like this. You can see that it's pulsing the EGR very evenly, meaning it's in a holding position. Known good waveforms. How do you find these known good waveforms? Use the information source in your shop. If it's not there, you can use the IATN.net. It's the International Automotive Technician Network. And it's a very comfortable website to use. You can go there, sign up free. And then if you become a sponsoring member, which is a very inexpensive fee, you can get known good waveforms. You can go to the waveform source and see all the waveforms that everybody's placed on them. And if you don't see the waveform you want and you make a known good waveform, then you can post it on there. Now, many DSOs have example waveforms stored right in the memory. Our DSO, for example, shows us what some known good waveforms look like. So, if you need to know how to test these circuits after you get the waveform, go to the diagnostic portion of this website and view the video of what you want to know how to test.